All right, this video covers conditional probability. This is a very specific type of probability that after the video, I hope you find this fairly easy. I'm going to teach you every trick I can. So first, let's start off with the definition of what is conditional probability. I actually wrote two statements here to help clarify what conditional probability is. The first statement is the probability of an event occurring given that another event has already known to have occurred. So the idea is now we're going to look at the probability that event A happens if we know that event B has already occurred. And that is the second definition I wrote here. It's the idea that, hey, we know that B has already occurred. What is the probability that A also occurs? Okay, so this is not the same thing as the probability of A and B, because find the probability of A and B is that they both happen simultaneously at the same time. They're both occurring. Here we're talking about, okay, if B already occurs, how does that change the probability of A? Now we have a notation here, and again we use a P for probability, and we're trying to find the probability of A, but here comes what's new. We put a line here. Now this line literally means given. So we say, what's the probability of A given that event B has already occurred? So this is a new notation. We're trying to find the probability of A given that B occurs. An example could be, okay, what is the probability you are a girl given you have a gray shirt on right now? So the idea is that the given is something I know. I know that the person has a gray shirt on. So that eliminates everybody else. You got a blue shirt on, you got a red shirt on, sorry, I don't care about you. I only care about people that have a gray shirt on because that was the given. Now I'm trying to find the probability of those people that are girls. Another example is, what's the probability you wear glasses given you are a boy? So once again, the given is what I already know. So I know that you are a boy, which means, sorry girls, I don't care about you for this problem. So I would ignore all girls. Now I'm only looking at the boys, and of those boys, I'm trying to find the probability that they have glasses on. That's the idea of conditional probability. Now the formula is actually pretty nice. The formula for A given B is equal to, it's a fraction now, and this should make sense after I done explain it. On top is the probability of A and B. So remember that upside down U is our symbol for and. And the denominator is the probability of the condition B. So in the numerator, it's the probability of A and B, and then the denominator, it's the probability of the condition B. Now again, this actually should make sense, because what's happening here is, let's go back to my example of trying to find the probability of a girl given she has a gray shirt on. So now that means my denominator is limited to only those people who have gray shirts. So if you have any other color shirt on right now, I don't care about you. You're no longer of my population, right? You're no longer somebody I care about. And then I'm going to take the people that have gray shirts on and are girls, and they go on top. So if you are a girl and you have a gray shirt on, then you are going to, be successful. You're going to make me happy. So I take the total people that meet both of those qualifications, and then I divide by the condition, which is having a gray shirt on. So again, it's a pretty easy formula. It works really well, but I'll be honest with you, sometimes you could just use common sense and you don't even really need that formula. And I will show you that by looking at our first example. So here's an example. We looked at 90 videos and we qualified them as content, meaning bad, okay, or awesome. And then we also looked at the quality of the video, low or high. So first question is kind of a review question. What's the probability that a video chosen at random is awesome? Well, that's easy. 38 videos are awesome. So that means I have 38 out of 90 videos to choose from. There's the probability of getting an awesome video. B, what is the probability a video is randomly selected that is high quality and awesome? Okay, well this is a little bit more specific. Now I'm talking about the 24 videos out of 90 that would make me happy, because these are the videos that are not only awesome, but they are also high quality. So that'd be 24 out of 90. So those are two very easy questions. But now we're going to move into this third question. Given a video is awesome, what is the probability it is high quality? So now we have a given, right? We're trying to find the probability it is high quality. I'll put HQ for high quality. Given we know the video is awesome. Now what this does is this limits me. I'm only caring about videos that are awesome. And of those videos, I'm looking for how many are high quality. Now, I'm going to use the formula here in 1 second, but I actually want to teach that you don't even need the formula. See, the given is 38. Meaning that 38 videos are awesome. So now my denominator becomes 38 because I only care about those 38 videos. Okay, bad, those videos I don't care about because the given is that it must be awesome. Now, of those 38 videos, 24 are also of high quality. So there is my final answer. Now, I do want to show you that the formula will arrive at that answer as well if you understand math. So on top goes high quality and awesome. Well, we actually already figured that out. 24 out of 90 videos are high quality and awesome. And the denominator goes the condition, awesome. There are 38 out of 90 awesome videos. Now, when I do the math, 24 out of 90, and instead of dividing by the fraction, I'm going to multiply by the reciprocal. Hope you've heard that term before. What happens is those 90s cancel, and I get 24 out of 38. So this proves that you can use the formula to get the answer, or you could just think about it. Given that it's awesome, which means I'm only allowed to look at the 38 awesome videos, 24 of which are also high quality, hence 24 out of 38. All right, second problem. This one involves no table, just words, which is why it's a good problem to look at. 40% of people read the USA Today newspaper. It is also known that 25% of people read the New York Times. And finally, we know that 5% of people read both newspapers. So the first question says, what is the probability that a person reads USA Today or New York Times? Once again, this is kind of a review question. The probability that you read USA Today or the New York Times, NYT would be using our formula. So we'd say, okay, the probability you read USA Today is 40%. Plus the probability you read the New York Times is 25%, but we got to be careful because that 5% overlap was amongst these 40%, but it was also amongst these 25%. So we want those 5% of people to count twice. We want them to count once, not twice. So when we do the math, 40% plus 25%, and then we subtract away that 5%, we get 40 plus 25 minus that 5. For the delay here is 60. So we get 0.60, or 60% of people read the USA Today or the New York Times. All right, now let's move into a conditional probability question because I see that word given. Given that a person reads the New York Times, what's the probability they read the USA Today? So I'm trying to find the probability that they read the USA Today, given I know that they read the New York Times. Now, this is how easy it is. Again, remember that formula. On top goes both. USA Today and New York Times. Well, I actually already know that. They told me that into the problem. I know that 5% of people read both newspaper. Now, on the denominator goes reading the New York Times. Well, actually, I was told that as well. 25% of people read the New York Times. Yeah, I know some of them read the USA Today as well, but I don't care. All I care about is the condition, 25% that read the New York Times. So all you got to do is divide these two numbers out, and you'll get your conditional probability. How easy was that? So 20% of people read USA Today, given they also read the New York Times. So hopefully you start to understand how these different conditional probabilities work. All right, let's move in. Went too far down, sorry. Let's move into another type of problem. Now, this type of problem seems confusing, but I'm going to teach you a really easy trick to help it make a lot of sense. At an airport, there are scanners that every bag must go through. If a bag has a gun, the alarm will sound 98% of the time. Now, we wish it was 100, but it is what it is. If a bag doesn't have a gun, sometimes the alarm still goes off 15% of the time. Now, the probability that a bag actually has a gun is 1%. What I want to teach you here is how to create a tree diagram to make these problems very easy. So I like to think about a bag. So here's my bag at the airport. Now, only 1% of bags actually contain a gun, which means that there is no gun in 99% of bags. Now, here's where the conditional part comes in. We know that if there is a gun, the alarm will go off, so the alarm will sound 98% of the time, which means that there is no alarm 2% of the time. Now, this is conditional because this number, this 98%, was on the condition that the gun is in the bag. Now, moving on to our next phase of this, we could say, okay, well, that also told us that if there is no gun in the bag, there is still a 15% chance that that alarm goes off, which means that there is no alarm 85% of the time if there is no gun. So you have to understand that, this scenario right here, gun in the bag and the alarm goes off, that is something that should happen, right? If there's a gun in the bag, we want that alarm to go off. Likewise, if there is no gun, we want no alarm, right? Those are the two good things. Now, I'm not trying to say a gun in the bag is a good thing, but in terms of it's doing the right thing. So these two things here, this is called a false negative. It's a negative, no alarm, when that's false. There should be an alarm. And this here is called a false positive, meaning that the alarm goes off, but it is a false alarm. It shouldn't be going off. Now, the questions on your paper ask you first, what is the probability that the alarm goes off? Now, that is not conditional. That is just very simple. What's the probability the alarm goes off? Now, when you think about a tree diagram, there are two branches that make the alarm go off. This branch right here, gun goes off. So gun in the bag and alarm goes off. Okay? Or there's this branch right here, no gun, 99 times the alarm still goes off 15. So there's two scenarios that could happen that trigger the alarm. So this is gun and alarm or no gun and alarm. So all I got to do is combine these two things. So 0.01 times 0.98 plus 0.99 times 0.15, and you should get 0.1583. So there's about a 15.83% chance that that alarm goes off. Now, the next question in your notes, it is what is the probability that there actually is a gun given that the alarm goes off? So the question says, given the alarm goes off, so that's what goes after the line, given that the alarm goes off, what's the probability that there really is a gun? So again, watch how easy this is if I use the formula. On top goes both, gun in bag and alarm goes off. That'd be gun in bag, 1%, and alarm goes off, 98%. Okay? Now, in the denominator goes the alarm goes off. Now, again, could be there's a gun, could be there's not a gun, I don't really care. The denominator is the condition the alarm goes off, which, conveniently, we've already figured out on top, which is why I set you up there. So the 0.1583 is the probability that the alarm goes off. Now, all I got to do is figure the final problem out. So 0.01 times 0.98 is 0.0098. Divide that by 0.1583, and I get a final answer of 0.0619. So if I hear that alarm go off in the airport, if I actually hear an alarm going off, there's only a 6.19% chance that there is actually a gun in that bag. Okay? Hopefully you see how the tree diagram made that problem easy. Let's do another problem very similar to that one. Prostate cancer affects 4% of men nationwide. A screening process is used to test men's blood for prostate cancer. If a man has prostate cancer, the test comes back positive 95% of the time. If the test is highly sensitive, however, so if a man doesn't have prostate cancer, sometimes the test still comes back positive 20% of the time. Create a tree diagram and answer the questions. So kind of like my bag problem, I'm going to start off with a man. Now, there is only a 4% chance that this man actually has prostate cancer, and that would mean that there is a 96% chance that there is no cancer. I just had to find the complement there. Now, it does say if you have cancer, the chance of a positive test result is 95%, which it should be, right? If you have cancer, you would hope for a positive result. But there is a chance of a false negative. A false negative would be the 5% chance that the test comes back negative even though you have cancer. Now, it says because the test is highly sensitive, you could even get a positive test result 20% of the time, even if you have no cancer, which means you should get a negative result if you have no cancer 80% of the time. So once again, this right here is what we call a false negative. It's a negative, but it's wrong. This is what we would call a false positive. It's a positive result that is wrong. Now, the first question says, what is the probability of a positive test result? Well, as you could see, there are two branches that lead to a positive test result. You could have cancer and get that positive test result, or here's another case where you could not have cancer and get that positive test result. So those are two cases that end with a positive test result. So Multiplying those together, 0.04 times 0.95 plus 0.96 times 0.20, you should come up with a perfect exact 0.23, or 23% chance that you get a positive result. Now the next question says, given that a test is positive, what's the probability you actually have cancer? So I'm trying to find the probability you actually have cancer given that a positive result came back. So the given always goes after the line. So to answer this, again, it's pretty easy. I'm just going to follow my formula. On top goes both cancer and positive. Well, that is one specific branch. Cancer, 4% times positive, 0.95. In the denominator goes the condition, getting a positive result. Again, nothing to do with cancer, just positive result. Any way you want it, positive result, which, again, conveniently, we already figured out above. So that would be the 0.23, the probability of getting a positive result. So all I got to do real quick is do 0.04 times 0.95, which is 0.038. Divide that by the 0.23 that you get a positive result, and I get a final answer of 0.1652. 0.1652. So hopefully you could take a second there, pause the video if you need to process that and understand what's happening there. So basically what happens is if you go in and you get a test and the test comes back positive, there is a 16.52% chance that you actually have cancer. Okay, moving on. Now this next problem is kind of a little bit of a trickier one, but I really like this problem. Okay. One letter from the sentence, live, life, king, size, is chosen in the following way. First, a word is chosen at random, and then a letter is chosen from the word. Now, I'm going to use a tree diagram. You don't necessarily need a tree diagram here, but I think it actually makes a lot of sense to help you understand this. So the first thing I'm going to do is choose a word. So I'm going to choose a word. I could choose the word live. I could choose the word life. I could choose the word king, and I could choose the word size. Now, once I pick a word, I'm going to pick one of the letters. So I have L, I, V, E that could be selected. I have L, I, F, E that could be selected. I have, sorry, I'm getting a little sloppy here. I could have K, I, N, G that gets selected, or finally S, I, Z, I'm getting really sloppy here, E. So if you think about it, a tree diagram is kind of nice because it shows you that there are 16 total options for what letter could get picked. 16 total options. You could pick the letter L by picking live first, L by life first, K by king first, and so forth. So you see the 16 options there. So now that we have this tree diagram, let's see how easy it is to answer this question. What is the probability that the word selected is king? Okay, all they want me to do is pick the word king. That's easy. 1 out of 4 words involve king, right? For me to pick the word king, there's a 1 out of 4 chance. There's 4 words. One of them is the word king. Now, another way I could arrive at that same answer is to think about my final result, right? If K, I, N, or G, if any of these 4 right here are picked from the word king, I'm happy. So I could have thought about the 4 outcomes out of 16 that involve the word king. Well, guess what that reduces to? 1/4. So either way you shake it, you get 1/4 as the probability of picking the word king. All right, what is the probability that the letter E is selected? Well, again, if I use my tree diagram, it's pretty easy. There's 1, 2, 3 ways that I could end up with the letter E. So that's 3 out of 16 that you can get the letter E. Now, if you like that, the tree diagram helps you, boy, oh boy, stick with it. But there is another way I could arrive at that answer. I just got to think, what needs to happen to get the letter E? Well, first, I have to pick the word live, life, or size. King would not work to get the letter E. So that's a 3/4 chance to pick one of those words. And then I need to pick the letter E. And in live, life, or size, I have a 1/4 chance to pick the letter E. So that would be 3 out of 16. What do you know? Another way to get that same answer. No matter where you shake it, that's how you get the 3/16. Now this last question is again, because I see that word given there, conditional. So I'm given that I get the letter E. So given that the letter E is picked, what's the probability that the word chosen was live? Now, I'm going to use the formula, but I'm also going to show you how you could use a little bit of common sense here. So I'm trying to find the probability that the word live is picked given that the letter E was selected. So on top goes live and E. Live and E. So I got to pick the word live and then get the letter E. So how could I think about that? Well, think about it. Look at my diagram here, right? There's only one branch that involves both the word live and the letter E. So there's only 1 out of 16 ways I can get the word live and the letter E picked. There it is right there. I circled it right here. Now, if you're like, I don't know if I like that, well, all I got to do is walk through it. I want to pick the word live, 1/4, and then pick the letter E. If I pick the word live, one of those 4 letters becomes the letter E. So again, I get 1/16. So it's, again, there's multiple ways to get that answer. Now in the denominator, I'm going to use my formula. So in the denominator goes the probability of getting the letter E, which we already found to be 3/16. So when I take 1/16 and multiply it by the reciprocal, 16/3, the 16s cancel, and I get a final answer of 1/3. Now, how else does this make complete sense? Well, if I picked the letter E, I must have had the word live, life, or size. If I know the letter E was picked, it had to be one of those 3 words, because the word king wouldn't work. That means there's 3 options that could have led to me picking an E, and one of them is the word live. Another way I could have ended up with 1/3. So conditional probability could be used with the formula, or it could be used with a little bit of common sense too. All right, last problem for conditional probability. Okay, a company manufacturing electronic components for home entertainment systems buys electrical connectors from 3 suppliers. The company prefers to use supplier A because only 1% of those connectors are defective, but supplier A can only deliver 70% of the connectors. Okay, so wait a minute. Now I'm starting to get a little bit lost. This is where a tree diagram will definitely help. So here is a connector. I don't know what a connector looks like, but maybe that's a connector. Okay, now I get my connectors from 3 locations, A, B, or C. The problem says that I get 70% of my connectors from A. Let me continue reading. The company must also purchase connectors from 2 other suppliers, 20% from B and the rest from C. Now that would have to be 10% because they have to add up to 100. So 70 and 20 is 90. The remaining 10% come from C. Now, I know that if you get a connector from A, there is a 1% chance it's defective, 99% chance it's not. Now, it goes on to say, the rates of defective connectors from B and C are 2 and 4% respectively. So for B, that would be 2% are defective, 98% are not. And then from C, 4% are defective, 96% are not. So the final question says, you buy one and it's defective. What's the probability it came from A? So this is like a given, but it didn't really say the word given, but it says you buy one and it's defective, which means you know it's defective. So it's given that we have a defective connector. I'm trying to find the probability it came from A. So let me go ahead and use my formula here. On top goes A and defective. Well, that is very, very specific. 70% chance it came from A times a 1% chance it's defective. There's my numerator. That was this very, very specific branch, A and defective. Now in the denominator goes the probability that you have a defective chip. Well, there are 1, 2, 3 branches that lead to a defective chip. So I got to consider all of them. The first option is A and defective. Or another option is B and defective. That's 20% times 2%. Or the last option would be C and defective. That is 10% times 4%. So now I got a lot to do here. Let me do the top first because that's pretty simple. 0.7 times 0.01 is 0.007, 007 there. On the bottom, I got to be careful. I'm going to do 0.7 times 0.01 plus 0.2 times 0.02, that's 20% B, 2% defective for B, plus 10% for C, times 0.04 for it being defective, which gives me 0.015. So there's only a 0.015% chance that a chip is defective, but I want to find the probability that that defective chip is A. So I'm going to take the 0.007 divided by the 0.015, and I get 0.4667. So now a lot of people don't understand that answer. They think, well, why is that so high? Well, you have to understand that first, it's very low chance to get a defective chip. There's only about a 1.5% chance to get a defective chip. But so many of my chips come from A that if it is a defective chip, because so many of my parts are already coming from company A, the chance is probably that it's going to be from company A. That's why the 46.67% is so high, because most of my chips come from A anyway. Even though A has a very low defective rate, I have a lot of chips from there. So hopefully you guys get the idea of conditional probability. I really hope it makes a lot of sense. Using the formula works, but in some cases you could kind of think yourself through it as well if you're a little bit careful. And don't forget about the tree diagrams that always make them easier in my opinion. All right, work on the worksheet that I gave you as well. See you guys in class.